Good morning, everyone. Thank you for joining this one-off event, this online seminar about numerical modeling for the design of ultra-high performance fiber-reinforced concrete structures. We, DNIFA, we are very honored and pleased to organize this event in collaboration with the Institute of Concrete and Science Technology, ICITECH, at the Universitat Politècnica de València. So during the whole event, your microphone will be muted to avoid any noise disturbance. You will have the possibility to raise your questions via the question box, so you can type the questions in this chat box. And at the end of every presentation, there will be a Q&A. And I will go through some of the questions and rate them to the speaker. My name is Jean-Claude. I will be the moderator, let's say, of this seminar today. I'd like to say a special thanks to my colleague Maziar Partobi, who has been organizing this event. And if we take a closer look to the program, the seminar will be, the first presentation will be at 9:40. So it will be a presentation of Eduardo Mezquida-Alcaraz on numerical modeling of ultra-high performance fiber-reinforced concrete from the material to the structure. It will be a 20-minute presentation, followed by 5-10 minutes Q&A. Then at 10 past 10, we will have a presentation from Professor Navarro-Gregori on numerical modeling of reinforced ultra-high performance fiber-reinforced concrete ties under serviceability conditions. Again, this will be roughly 20 minutes presentation, followed by a Q&A. Then at 10:40, from 10:40 to 11, we will have a small coffee break. So you will be able to grab a cup of coffee or just have a little break. Then we continue at 11 a.m. with a presentation from Carlos Lazaro on active bending in ultra-high performance fiber-reinforced concrete structures. Again, this will take roughly 20 minutes, plus 5 to 10 minutes Q&A. And at 11:30, it will be the last presentation from Professor Serna. So again, on the ultra-high performance fiber-reinforced concrete, from material concept to structural design for efficient application. And at 12, we will have a roundup, and I will close this online seminar. So this is the program for this morning. So the first presentation, which will be starting in 4 minutes, will be given by Dr. Eduardo Mezquida-Alcaraz. His research interests include development of nonlinear finite element modeling for concrete structures. And his recent investigation have focused on numerical modeling and experimental characterization of ultra-high performance fiber-reinforced concrete and fiber-reinforced concrete for structural analysis. So I suggest that you start, Eduardo. I think we are just on time, so the floor is yours.
Okay, thank you very much. So my name is Eduardo Mezquida, and I am going to do the presentation called Numerical Modeling of UHPFRC from the material to the structure. Yes. So first of all, I will start with an introduction trying to define the concept of UHPFRC, how it could be characterized for tensile behavior, and how the standards considered it, the main standards worldwide. So ultra-high performance fiber-reinforced concrete could be considered an advanced modernization of fiber-reinforced concrete that, due to its particular dosage and casting process, it is able to develop enhanced properties such as compressive strength, close to 150 megapascals, tensile strength more than 7 megapascals, flexural strength in between 15 and 40 megapascals, strain hardening with the idea of developing multiple cracking, self-compacting, ductility, durability, and all of them could lead to the design of slender lightweight structures. But the question is, it is necessary strain hardening for developing multiple cracking? It is economically competitive? It is always possible to develop to design slender lightweight structures. What happens with properties such as the shrinkage? If we see the tensile behavior of UHPFRC, we can. It is usually characterized by means of a stress-strain crack opening relationship, where we can differentiate two main parts. From the peak, considering this peak as the ultimate tensile strength, we can define the pre-peak domain and the post-peak domain. In the pre-peak domain, we can find the elastic and the multiple cracking behavior that defines the volumetric energy, as it implies all the volume of the specimen in the process. This is defined by means of a stress-strain relationship. From the peak onwards, we have the softening branch, where the macro crack opening development takes place, and the energy released is considered the surfacic energy as it is released in the surface of the crack. If we compare this, the constitutive behavior of UHPFRC to the conventional fiber reinforced concrete, we can see that the characteristic volumetric energy of this UHPFRC concrete is usually neglected for the case of fiber reinforced concrete. If we see how the UHPFRC is characterized in the main standards worldwide, we can see that the tensile constitutive behavior is expressed or is proposed by means of a stress-strain relationship with, or a stress-strain crack opening relationship with elastic and perfect plastic behavior, strain hardening, even low strain softening for the part of stress-strain. And to characterize experimentally or to obtain experimentally this tensile behavior, it is usually proposed uniaxial tensile tests mainly and bending tests. For the case of uniaxial tensile tests, we can obtain directly from this test the tensile constitutive behavior, but they are challenging to perform as they are very sensitive to the setup. On the other hand, concerning the bending test, they are more easy to perform and they are an easier alternative to this tensile test. But we need to use inverse analysis methods to obtain the tensile behavior from the bending test, from the bending curve obtained from the bending test. If we see, for example, the French standard, they propose as experimental test, bending test, direct tensile test, or not diabolos, depending on the type of structure and the constitutive behavior. And they consider as constitutive behavior strain hardening or strain softening. And they propose a simplification for design, for example, for the case of strain hardening by means of a stress-strain relationship with the strain hardening, and for the case of strain softening, for both mechanical possibilities, they propose a simplification for design by means of a stress-strain relationship with strain softening. In our research group, we developed a direct procedure for UHPFRC tensile characterization from the strain softening to the strain hardening range. And in this sense, we are able to obtain the tensile parameters that we use for modeling and design. I will explain this direct procedure based on the material models proposed, then how this direct procedure works, and then how it is calibrated and validated using a numerical model. Our proposal is based on the same classification as the French standard, but we consider to define the strain hardening behavior as stress-strain relationship for the volumetric energy and the stress crack opening relationship for the surfacic energy. And for the case of strain softening, for both possibilities, we make a simplification considering a stress-strain relationship for the what could be considered something in between the volumetric energy and the surfacic energy. As we have the macro crack position here, we also consider that it is possible to develop a microcracking phase till this point where the macrocrack process and the macrocrack opening develops. And this part is expressed by means of stress crack opening behavior. So our stress-strain softening behavior, we consider that we have this possibility when in tensile test, we have something in between strain softening and strain hardening. And in bending, we always have deflection hardening. And we consider that we have strain hardening when in the tensile test, in the tensile behavior, we always have strain hardening, and in bending, we always have deflection hardening. Our direct procedure starts from the 4-point bending test, the unreinforced 4-point bending test. So from this unreinforced 4-point bending test, we obtain the bending curve, the bending experimental curve, and we define 4 specific key points. From these 4 specific key points, we are able to obtain the tensile parameters necessary for numerical modeling using an inverse analysis and a softening correction. So to validate and calibrate our nonlinear, our direct procedure, we carried out an experimental program of unreinforced 4-point bending test, considering a different amount of fibers to get a wide range from strain softening to strain hardening behavior. As we can see here, we obtain the experimental bending curve from the bending test. We apply our 4-point inverse analysis and the softening correction, and we obtain the tensile behavior and the tensile parameters that we need for numerical modeling. To build our numerical model of the 4-point bending test, we define 2 different approaches, the smear cracking approach and the discrete cracking approach. For the discrete cracking approach, as this is a continuum model, we need to distribute the crack opening part of the curve, this is the surfacic energy, into a mean strain considering the material crack bandwidth. But we don't know which is the material crack bandwidth of UHPFRC. So for our nonlinear finite element model, we assume that the length of the finite element equals the crack band, with the idea of preserving as much as possible the energy in the transformation. So as we can see, our smear cracking approach is mesh size dependent. We define 3 different element sizes. And also we define or we create a random algorithm to vary randomly the tensile stress of UHPFRC. In this sense, we are able to vary the position of the macro crack randomly for this smear cracking approach. When we see the results, when we compare the results from the simulation to the experimental, we can see how our numerical model for the 3 element sizes, and using the different runs of the random analysis, we are able to simulate with good accuracy the elastic and the deflection hardening part of the curve. And even for these 2 element sizes, we are able to set the maximum bending strength. But as we can see, we are not able to simulate accurately or with reliability the softening part of the curve. Also, if we see this picture, we obtain different results depending on the analysis strategy followed, as we define an incremental iterative procedure to our nonlinear analysis. So the smear cracking approach is sensitive to the element size and also to the analysis strategy. Alternatively, we define the discrete cracking approach. This discrete cracking approach in this discrete cracking approach, we consider that all the specimen is considered as a continuum body. So we need to model this part with a continuum material model. In this case, we use the smear cracking approach previously defined, but we set the position of the macro crack in the mid-span section. This is, we set the crack path by means of interface elements defined with a stress crack opening relationship. When we compare the results from the discrete cracking approach, the smeared and the experimental, we can see how the discrete cracking approach is able to simulate with good accuracy all the curve, all the experimental bending curve from the unreinforced 4-point bending test. So to validate our direct procedure, the discrete cracking approach is the best option. Once we have validated and calibrated, and we have defined a direct procedure to obtain with reliability the tensile parameters that we need for numerical modeling, a step forward to the structural modeling could be to model flexural reinforced beams. In this sense, we carried out an experimental program of short beams composed by longitudinal reinforcement bars, and we placed stirrups to avoid the shear failure. We cast these beams using different amount of fibers with the idea of developing a wide range of strain softening to strain hardening behavior, and we test these beams into a 4-point bending test. Also, we carried out, we cast two long beams of 4.5 meters length with two longitudinal reinforcement bars placed on the bottom face of the beam with 20 millimeters diameters for the first specimen and 16 millimeters diameters for the second. And these long beams were tested also at 4-point bending test. And together with the short beams and the long beam, we cast unreinforced 4-point bending test specimens to characterize the tensile behavior of the UHPFRC used to cast the beams. In this sense, we can see that we obtain, if we consider this gamma parameter as the hardening ratio, this is the relation between the ultimate tensile strength and the tensile stress obtained from the direct procedure. We obtain a wide range from strain softening to strain hardening for both amount of fibers. So for modeling the reinforced beams, we apply our direct procedure to obtain the tensile parameters. This is from the unreinforced 4-point bending test cast together with the beams. From the experimental bending curves, we obtain the tensile parameters using our 4-point inverse analysis and the softening correction. And these tensile parameters are used in the smear cracking approach and the discrete cracking approach to define the numerical model. We build the model with 2D and 3D using the smear cracking approach and the discrete cracking approach. Also, for the reinforcement, we used a stress-strain relationship with the strain hardening. And for the bond between UHPFRC and reinforcement steel, we use a shear traction slip curve by means of door. If we see the results, we can see how the simulation of the reinforced 4-point bending test of the reinforced beam, these continuous lines that represents the model when they are compared to the continuous one that is the experimental for the 3 percentiles, our results are very accurate. So the model is very accurate and reliable for both amount of fibers. Also, if we compare the 3D model to the 2D model using the discrete cracking approach and the smear cracking approach to the experimental, we can see how the results are very close due to the influence of the longitudinal reinforcement. This is the opposite as we obtained when we model the unreinforced 4-point bending test, as we had a very big difference between the discrete and the smear cracking approach, especially for the softening part. Also, we are able to calibrate with our nonlinear finite element model the shrinkage influence of UHPFRC. This is a numerical calibration. So previous the test starts only because of the storage of the beams between they are cast and they are tested. So previous the test start, we have the shrinkage influence close to the position where the reinforcements are placed. This is the reinforcement are making a restriction of the free contraction of the UHPFRC. This is translated into a pre-stress in tension for the UHPFRC close to the reinforcement and a pre-compression of the reinforcement bars previous the test start. Also, we are able to simulate the cracking pattern of the UHPFRC depending on the hardening ratio. This is, here we represent four specimens with a strain hardening, cast with UHPFRC with a strain hardening, less strain hardening, strain softening, and more strain softening. If we see the cracking pattern at the microcracking stabilization phase, we can see that for the case of a strain hardening ratio, we have a very distributed cracking pattern. And this cracking pattern is also distributed for the case of strain softening, but in this particular case is more concentrated in certain zones. If we see the collapse moment, at collapse level, for the case of strain hardening, we still have a distributed cracking pattern more concentrated in the mid-span section. But if we see the strain softening behavior, we have a big crack as a consequence of a coalescence from a previous concentration zone in the microcracking stabilization phase. Also, we modeled the long beams using our discrete cracking approach, as it is the same result from the smear cracking approach, or very similar as we checked before for reinforced beams. And we can see that we are able to simulate very accurate the 4-point bending test of the long beams. And also we are able to calibrate the shrinkage strain. This is the shrinkage effect. As we can see here, we obtain, if we analyze the cracking pattern of the long beams, we can see that for the first specimen, we obtain from the direct procedure, when we apply the direct procedure to the unreinforced 4-point bending test specimen cast together with these beams, with this particular beam, we obtain that it exhibits a strain hardening behavior. So, as we can see, the cracking pattern is very distributed for the case of for the stage of microcracking stabilization, and this is also transmitted in a distributed stress pattern at the reinforcement. If we see the collapse, we have still a very distributed cracking pattern, more concentrated in the mid-span section, but we still have a very distributed stress pattern in the reinforcement. If we see the second long beam, as it exhibits a strain softening from the direct procedure applied to the unreinforced 4-point bending test casted together with this beam, we obtain a distributed cracking pattern at the microcracking stabilization phase, more concentrated at certain zones, and it is transmitted to the reinforcement by means of a distributed stress pattern. But when we reach the collapse, we have a big coalescence into big macro cracks as a consequence of the coalescence from previous concentration. And this is transmitted in this sense to a local concentration of stresses in the reinforcement, where it at the same position of the macro cracks. So, as a conclusion, a simple and easy to conduct direct procedure to characterize the tensile UHPFRC behavior is defined for nonlinear numerical modeling and design, covering all range from strain softening to strain hardening UHPFRC constituted tensile behavior. When using tensile parameters from direct procedure for modeling reinforced UHPFRC flexural elements, the nonlinear finite element model reproduces with good sense and coherence the crack pattern depending on the tensile UHPFRC behavior. This is strain softening or strain hardening. And using the nonlinear finite element model, the shrinkage influence can be numerically adjusted. Thank you very much.
Well, thank you very much, Eduardo, for this very nice and very comprehensive presentation. And it's also nice to see our software Diana in action, I would say. Let me see if there are any questions. So as I mentioned, you can raise or drop your question in the question box, and I will read them and Eduardo will answer. So there is a question from Charles Kanji. I hope my pronunciation is correct. What is the volume ratio or percentage of the steel fibers for the two dosage, so 130 kilogram per cubic meter and 160 kilogram per cubic meter?
This is the percentage of fibers used in this research, right? Is that the question?
Volume ratio or percentage of the steel fibers for the two dosage?
Yes,
at 130 and 160.
Yes, between 1.5 and 2%.
Okay. I hope it answers your question, Charles. Yes, thank you for that. Are there more questions?
Thank you.
Of course, you can address your question later, and we can, of course, share them with Eduardo, so he will have more time to elaborate his answer after the seminar. Yeah, let me see. There are another question coming from Abhijit Kulkarni. So which concrete material model was used to model the ultra-high performance fiber reinforced concrete beams in Diana?
The total strain crack model.
Okay, very good.
I use the total strain with the hypothesis, in this sense, with the smear cracking approach, and then we adapt a discrete cracking approach. But the basis is the total strain crack model.
Thank you. There are two more questions coming from Osama Hahid. After the inverse analysis to derive the constitutive model for the ultra-high performance fiber reinforced concrete, what was the factor that was applied? Does it reduce the strength? So it's a double question, actually.
Can you repeat the end of the question?
So after the inverse analysis,
yes,
to derive the constitutive model for the ultra-high performance fiber reinforced concrete, what was the factor that was applied? And does it reduce the strength? It's a double question.
Well, I only for modeling we only use the tensile parameters obtained from the 4-point inverse analysis, and we define point by point in our tensile in our numerical model, but we didn't use any factor. No. Only we use a factor for the random analysis, but we define the random analysis taking into account our standard deviation from the tests to calibrate more or less the possible variation.
Okay, well, I hope it answers your question, Osama. If not, don't hesitate to drop us an email and elaborate a bit more, and I will be more than happy to share the question with Eduardo. So let me see, because there are more questions. There is a question from Juan Antonio Rodriguez. How do you take into account the fiber orientation in the model?
We didn't take it into account. We considered it in the variation of the experimental tests, in the variation of the standard deviation and the parameters as we carried out a lot of tests. We consider that it is included in the 4-point inverse analysis parameters, but it could be a good idea to model maybe the fibers individually or or to assume a parameter of like the French standard, but we consider it into our variation without any parameter else.
Okay, thank you. There is one more question, again from Osama Haid, who is very interested on the topic. Have you tried applied this nonlinear finite element approach to specimens failing in shear?
Yes, that is the following step. We only apply this for normal forces. This is axial and bending, but the following step is with shear. If you see, for the reinforcement beams, we for the short ones we placed stirrups to avoid that shear failure. We only want to in this part, it is a previous first step. So in this first step, we only try with bending and axial forces.
Okay, that's very good. Thank you. Let me see more questions for Eduardo. There was a question from Giovanni Volpati. So you didn't mention model code 2010 models. And the question is, are these model more precise?
Well, the model code, I think it's only for fibers, not for, well, it is I mentioned the most known codes for UHPFRC. Maybe in the model code we can find any reference, but it is more developing in the codes that I showed. I think maybe there are several recommendations and things like, but I only said the most known code.
Okay. Thank you, Eduardo.
Thank you.
Well, next to the question, Eduardo, I must say that there's a lot of compliment coming for the quality of your presentation. So I think it's also important to rate that. So a lot of people are saying a big thanks to you for the presentation. So
thank you very much.
I cannot applaud, but I wanted to share this positive feedback. So I think we are done with you, Eduardo. Thank you very much for this very nice presentation. And we will now continue with the next presentation, which will be with Professor Juan Navarro-Gregori. His research interests include development of nonlinear analysis procedure for concrete structures, and his recent investigation have focused on numerical modeling and design application of the ultra-high performance fiber reinforced concrete. So let me make you presenter.
Okay, thank you very much, Jean-Claude. And thank you for all you attending this presentation, and for the Diana colleagues for letting us to do this seminar. We are very pleased to have the opportunity to give these presentations. Well, my name is Juan Navarro. I'm from ICITECH Institute, Universitat Politècnica de València in Spain. So this is a presentation that will go on a little bit what my colleague Eduardo Mezquida has just explained. And now we will study which are the benefits of combining a concrete with very good properties in tension, as it is the ultra-high performance fiber reinforced concrete. Now combining with the traditional reinforcement bars, studying the tensile behavior. Well, this work is mainly based in the doctoral thesis by Eduardo that developed the numerical modeling, and another doctoral student called Majid Korami that performed experimental tests of the elements I'm going to show now. Okay. Well, I would like to say that the potential use of the ultra-high performance fiber reinforced concrete received a lot of attention quite a long time ago, when it was built the first footbridge made with this material in the world. This was the Sherbrooke footbridge in Canada in 1997. It was a key point to draw the mind of to engineers to new ideas for design, new innovative forms of construction, and then to start to break with the traditional ideas of a structural design with traditional concrete or steel. With the UHPFRC material, it is possible to design light thin structural elements, as this example shows. And if we compare with similar structural elements made of conventional concrete, since this material is very, very expensive, the initial costs of the materials itself have to be covered by an important reduction of the section. And the total cost of reduction should also include the benefits of cheaper transport, since these are lightweight structures, and the improvement or the enhancement of their durability. Well, with this idea of compensating the overall costs of a structure made of this concrete compared to traditional solutions, it was designed in our research group some years ago, the footbridge over Las Ovejas ravine in 2014 in Alicante, in Spain. It was the first structure of this kind in my country. So we ended up in a very light solution based on the concept of the truss, which is a very efficient structural system. So with this concrete, it's now possible to design elements not only working on compression, but also working under tensile forces. But some questions arise here. These questions are questions like how these tensile elements really behave, or should we include longitudinal reinforcement in them? It seems that it has to be that way. Or how is the combination between the rebars and the concrete, aspects like tension stiffening, shrinkage, or the special type of cracks that this concrete develops. So this was the reason to carry out an investigation on the serviceability behavior of reinforced UHPFRC tensile elements, focusing our attention on the serviceability conditions. So we proposed a test system for carrying out experimental tests of the reinforced UHPFRC ties under these serviceability laws. We never reached the collapse of the element. So to apply the tensile force in this experimental test, we use a specific gripping system, which include two steel jaws. The specimen was installed in a steel frame, and the specimen was pulled out with an hydraulic jack, and the tensile force was controlled by a load safe placed between the main plate and the end of the rebar. The specimens were made to take a square cross section with a central reinforcement bar, and the specimen was 1 meter length, and the rebar was extended 225 millimeters to let the gripping system to pull out the specimen. But two complementary rebars were welded to the main rebar in order to connect the concrete specimen to the steel jaws and avoid local failures at the gripping system. The longitudinal 8 displacement transducers were installed on the specimen surfaces to record the element elongation and to have the measurement of the average longitudinal strain at any load level. Well, the program was composed by 3 cross sections, 60, 80, and 100 millimeters of size, and 2 reinforcements diameter, 2 rebar diameters of 10 and 12 millimeters, ending up in 6 different reinforcement ratios, and several specimens were made with for each case. The nominal yield of the bars were traditional bars, not specific bars, only traditional with 500 megapascals. And the fiber dosage used in this case, it was 160 kilos per cubic meter of small steel fibers with a diameter of 0.2 millimeters and a length of 13 millimeters. An overall view of the results give us there is a similar pattern for all the cases studied. If we compare the equivalent normal stress carried by the whole tensile element, and here we represent the average strain, we always had a first stage with an elastic and cracked behavior right at the beginning, a second stage where the concrete matrix cracks, and that can be defined as the micro crack formation stage, and after that, a third stage of microcrack stabilization, which is characterized by a relatively constant slope, and a slope which increases with higher reinforcement ratios, as it is seen in the picture. Well, in the following slide, I will show from the whole response of the ties. If we subtract the load carried out by the reinforcement, we can obtain the concrete contribution of the UHPFRC. So experimentally, we obtain after the micro cracking average tensile stresses in the concrete in between ranging from 7 to nearly 10 megapascals under the micro cracking stabilization stage. And now I'm showing an example of the cracking pattern obtained for one of the specimens tested. It can be seen how, thanks to the presence of the longitudinal reinforcement, a state of control microcracking was able to be maintained throughout the test. In this case, we did not reach more than 2 per mil in average elongation. At the end of the test, after unloading the test, the number of cracks was recorded by wetting the surfaces with water, and combining the number of cracks with the elongation measured, it can be evaluated the average crack width. So the values obtained for this type of concrete with reinforcement are really small, which are very good news for durability design. And the average crack opening always achieved was lower than 0.5 millimeters. Well, with this, I just finished a brief presentation of the experimental program. I don't give you more details, and will now go on with the numerical modeling of this presentation, which is the main focus of my talk. Well, as I'm saying, now I'm going to present how to model numerically the experimental behavior of the reinforced UHPFRC ties, considering such important effects as tension, stiffening, or shrinkage in the model. Well, first of all, as Eduardo was mentioning in the previous presentation, it is necessary to characterize the mechanical behavior of the UHPFRC, and we are doing that in our group by means of an inverse analysis based on the 4-point inverse analysis. So here in this figure, we can observe the sigma deflation curves corresponding to the average and characteristic values of the bending test. Here I'm representing the flexural stress. Let's take note that we are getting values for the characteristic curve up to 21 megapascals and a little bit more than 50 megapascals for the characteristic. But after applying the inverse analysis, as these are tensile properties, the results, for instance, for average values, give us a FT value of 0.62 or a strength value of 8.444, which is far less the equivalent bending stress. And in any case, in this, we are dealing here with a concrete that can be characterized as a strain softening behavior in tension. Well, with this characterization, we have developed two different models, a 2D model and a 3D model, to characterize these ties, UHPFRC ties. Well, in the case of the 2D model, we have used the software of Diana. The tensile elements have been modeled with 2D quadratic plane stress elements with 10 millimeters of size. And the material model used was based in the smear cracking approach, and the fixed total strain crack model expressed according to the crack opening curve that we have. And the material model used, we used one of them available in the program. We adapted the corresponding to the fiber reinforced concrete using the crack opening based relationship. The material model used for the rebars is the von Mises strain hardening elastoplastic behavior for the steel with a bond slip behavior according to the door constitutive model implemented also in the software. This is for the 2D case. And for the 3D model, it's a much more complex model. The tensile elements here are modeled with 3D quadratic isoparametric solid brick elements, in this case with 20 millimeters. And between them, this is every 20 millimeters, we have included quadratic plane 3D interface elements every 20 millimeters along the length in order to simulate the micro cracking effect. Okay. Moreover, in order to have a better representation of the reality in the experimental test, as we know that the properties of the concrete are not always really constant, a random field that multiplies the values of the UHPFRC tensile behavior has been added to better model this scatter, and the FRC factors used for the random field have been adjusted based on the variability of the results obtained in the characterization process. Well, with this model, and it is important to pay attention to the following aspect, which is the UHPFRC shrinkage. So I must mention that it's totally necessary to include this effect when dealing with reinforced UHPFRC elements. And the shrinkage effect is taken into account as a material function when defining the total strain crack model. So all these functions are available in the software, and the shrinkage value is based, in our case, on the function directly proposed by Eurocode 2, but this is for normal concrete, and it was incremented in a percentage as numerical adjustment to take into account the UHPFRC. Well, in the following slide, I'm showing one result of one of the specimens. Is the results of the numerical validation of a specimen of 60 millimeters and a rebar of 10 millimeters. We see that the results are in between the line, which is the uncracked section, this one, and this two, which is the response of a bare bar. So there are, if the results of the experimental test compared to the 2D and the 3D model are quite accurate in the serviceability behavior, and we can say that there are a good fit between both of them. The different cracking stages of the tie are well detected. This is the uncrack, the microcrack formation, and also the stabilized microcracking. And the only thing is, if we compare the 2D and the 3D model, is that the fit due to the effect of shrinkage is a little bit different. In this case, the increment of the percentage increment for the case of the Eurocode 2 was 50% for the 2D case, but only the 2D 20% for the 3D case. That it means that the 3D effects that this tensile test has is important, so we could say that this is the more accurate and precise model to characterize these tensile elements. If we now see some other comparisons for other specimen tests in the experimental program, in general terms, you can see that the same effects can be observed. A good fit in general terms, the three cracking stages are well detected, and some differences between the fits due to the effect of shrinkage, being less in the case of 3D. Well, at this point, I will focus more on the 3D model. And here I'm showing an example. And now in this slide, my objective is to show in detail how the model is to simulate with reliability the different stages of the experimental test. Now here I'm showing the stresses in the concrete due to the shrinkage effect. This is at 30 days, just before the test was done. Here we can see the stresses in the normal direction for the brick elements and also for the interface elements. The results are very close. And we have here a significant tensile stresses due to the shrinkage. And the reinforcement gets compression stresses because interacts with the concrete. Well, now this is a animation of this shrinkage effect from day 0 to day 30, where we can see how the normal stresses evolve and we can see that the concentration of stresses is mainly in these parts. As a result, that here we have 3 rebars, and in the middle we have just 1 rebar. In the area where the rebars are present with the 3 bar, we get here around 5 megapascals, and here about 2-3 megapascals. And this numerical models help us to limit the stress regularization zone in the specimen, which is approximately, in this case, located in the central third of the type. Now, if we go on to the microcrack stabilization stage at 90 kilonewtons, we see here the evolution of the normal stresses in the concrete and in the reinforcement. And in this case, all the matrix is cracked, and we can see we've focused our attention on the stress flow in principal directions. We see here certain localized crack formation in different sections, and this is mainly due because we are dealing in this particular case with concrete with some strain softening. In the following slide, I'm representing now the crack openings in the longitudinal direction. All 4 figures represent the same property, but with different scales or views, and 2 main effects we can observe. The first one is the crack opening varies along the specimen. It's not a uniform distribution. And moreover, if we see the detail in the section, across the section, the crack opening does not achieve all the section. And this can be something weird but this is due to the random field that was used in the characterization, and it's quite similar to what we usually see when we did the experimental test. Okay, now we can, as we included the bond slip element, the interface bond slip stresses, I'm showing here those stresses, and there are peaks of these stresses, even with values positive and negative values, which is given a good sense of what's happening inside the type. And to end up with this detailed analysis of microcrack stabilization stage at 90 kilonewtons, I'm showing the distribution of longitudinal stresses in the reinforcement bar. And similar to what happened in the previous slide, it is interesting here to see that there is not a uniform distribution of longitudinal stresses. There are certain peaks. And this slide and the other one, the previous one, support the idea that there are areas along the specimen that are more damaged or cracked than others. Well, I will now show 2 animations of the behavior of the specimen from the beginning of the test to the collapsed level numerically, because we didn't arrive to the collapsed level. Here I'm showing the normal stresses. Sorry. No, this is not, sorry, this is the normal stresses, okay. And how this evolve along the whole path up to the collapse, and how the program is able to achieve go through all the parts of the normal stresses characterization that we have done. And for the reinforcement, we see how the reinforcement is able, in a scale between 0 and 560 megapascals, to carry out the stress and to interchange the stresses between the rebars and the main rebar and the 2 rebars in the borders. Well, to end up, I will show you also 2 animations of the evolution of the cracks from the beginning of the test to the collapsed level. In this case, the first one, the whole specimen is shown, so that only the evolution of the crack openings on the surface can be seen. And in the last one, the second animation, we show in detail evolution of the openings, but allowing now to see what happens inside the specimen. Well, with this, I will conclude my presentation with some conclusions. The numerical model developed, reproduced with sense and coherence of the stages, the shrinkage effect, the elastic microcrack formation, and stabilized microcrack in the stages. Shear influence is very important and can be adjusted with the model, and the internal tensile stresses can be considered. The importance of the influence of the 3D effects of this for this test, this specific test. The numerical model is able to overcome local instabilities generated by differences in stiffness due to the variation of reinforcement, which was not an easy task to obtain. And results demonstrates both the reliability of the model developed, the numerical model developed, and the coherence of the tensile UHPFRC material characterization process. Finally, I would like to say that Diana software has provided us the necessary numerical support and the tools to carry out this numerical modeling, including all the effects in a proper way. Well, now what next? So now it's time to go one step further and just to move on to real UHPFRC structures. That will be the following step in our group. Well, with this, I conclude my presentation. I hope you all found it interesting. Thank you very much for your attention, and I remain at your disposal for any questions you may have. Thank you.
Well, thank you, Owen, for this very nice and very comprehensive presentation. It was also nice to see that you included some Diana animation. I find it very illustrative for the purpose. So let's see if there are any questions. So just like you did for the previous presentation, you can drop your question in the chat box, and I will read them to Professor Navarro-Gregori. What people are typing mainly, it's to raise the fact that it was a very interesting presentation with a high quality talk. So it's all positive, I would say. And some questions are coming, one. So there is a question from Alok Dua. Can high strain rate effects be included into the material model?
So, if I high strain rates?
Yeah, can high strain rate effects can be included into the material model?
I guess it could be introduced in the material model, but we have not worked with this high strain rate. We just the model we only have proof for this concrete, not for in other combinations. So I guess it will be possible, but we have not tried with that. So I think we have to investigate in that.
There is one more question coming from Rad Abdulaziz. How to know if there will be softening or hardening?
That's a very good question. That's one thing that has. What happens is that strain, as this is a very expensive concrete. If we include a lot of fibers, good fibers, finally, is for sure we will have a strain hardening behavior. But this depends on the dosages. Okay, so what happens is that in our case in Spain, as it is like an expensive material, what we try to do is to use a low amount of fibers. So with 160 or 130, we are in the border between the strain hardening and the strain softening. Okay, so it is not possible if you don't characterize your concrete beforehand to know exactly if it is one kind of the other. So it's necessary to do this bending test to characterize with several specimens and to obtain finally some values that finally gives you a strain softening or strain hardening material. But that depends on the production of your concrete and your quality of production in your, and with the characterization process, you finally are able to know if you have one type or another of UHPFRC.
Okay, thank you very much. There is one more question coming from Thomas Maleska, and his question is, why did you use interface element?
Well, the thing is, as when there is a softening, we can take that softening with in the smear cracking approach or the discrete cracking approach. After doing the first models with UHPFRC that were with the bending test that Eduardo told before, the thing is that when we have a strength softening, we were more confident on an interface where we control that crack. So these are interfaces that don't start to work up to the peak stress, and onwards they work. So it was to have a mesoscale, a more detailed, precise model to obtain the effect of the cracking. The overall response, it was for an overall response is a 2D model could be enough, mainly when you have reinforcement. But if you want to be detailed, and we were more confident in a much more complex model with the interface elements. But both possibilities could be depending on what you want to focus on.
Okay, thank you very much, Juan. Let me pick up a last question from Giovanni Volpati. How do you compare your approach with the closed form approaches proposed by Professor Mobasher?
Okay, well, that's more a question of characterization, right? So my opinion is that when you have a bending test and you have an inverse analysis, finally it's a mathematical tool or to derive the options. So the question will be, okay, let's have the same specimens and we can use an inverse analysis like the Professor Mobasher, that we all very well know that approach, a very good approach. Our approach is slightly a bit different, but all approach could be good. So finally, are ways of obtaining the tensile properties. Our proposal is very straightforward, but but it's also based in our case in a closed form formulation like the Professor Mobasher. So I guess if all of them are well done, the results of the characterization process should give the same results. So it's not I don't think it's a problem.
Okay. Well, thank you very much, Juan, and I want again to share all the positive feedback that is written in the chat box. So people were very impressed by the quality of your presentation. So they are saying a big thanks to you. That's very much the presentation was very well received. So thank you for that, Professor
Thank
Navarro.
you to you for the colleagues of Diana for the opportunity. Thank you.
Let's continue with our online seminar. The next lecturer will be Professor Carlos Lazaro. His research interest covers the application of fiber-reinforced concrete for architectural shells, the use of recycled concrete in bridges, the mechanical modeling of lightweight, deployable and very flexible structures, and more recently, the design of structures using bending as shape-driving paradigm.
Okay, so thank you very much, Jean-Claude. Thank you for letting me participate in this nice seminar organized by Diana. And my name is Carlos Lazaro, and I work in the Department of Structural Engineering or Structural Analysis in the Universitat Politècnica de València. And my talk is about active bending in UHPFRC structures. And the first question is, but what is active bending? Because this is not, maybe it is not a very common topic, and I will try to explain it as fast as possible. In this case, using this beautiful illustration by a Japanese artist named Hokusai, in which you can see several archers using their weapons. And if you look at one of these bows, of these weapons, you can see how the string of the bow is making or introducing some bending in the rod of the bow, and by pulling the string, that means by introducing some additional tension, you can increase the curvature of the bow, and in this way you can change the shape of the bow. And this philosophy of shaping structures through bending, it is the philosophy of the so-called active bending structures. So we want the structure to acquire a better shape, a more suitable shape to resist the loads. And it is also a way, a kind of step forward to build lighter structures. So this is our ultimate goal, to build lighter structures by using bending as a shape driving pattern. And in this process of bending, the structure is storing elastic energy, and we also can think of cable tensioning, adding some geometric stiffness because of the tension in the cable, but it has also a price that we have to pay. So part of the material strength is used in the shaping process, and also we need to ensure that a structure built with this principle has to be stable, because if you look at the upper part of my slide, you see that the process may resemble the same process that makes a rod buckle. And of course, we don't want the structure to buckle. We have to stabilize the structure once we have reached the target configuration. This is the overall concept, and we can now look into the history and try to find early examples of this principle. And perhaps the first application of this principle in the modern history of construction is the Crystal Palace, built by Paxton in the mid-19th century, where he used the so-called Paxton gutters or gutter beams that you can see in the middle of the image. And they are timber beams, U-shaped timber beams, and they are pre-cambered, so they are pre-curved by the action of a lower metal rod, and this metal rod was put in tension, and by means of two deviators, Paxton introduced some curvature in the timber, in the wooden beam. This helped the gutter functionality, it helped the water flow, but also produced a curved shape that helped resist the weight of the roof that was also resting on the gutter beam. And the tension of the rod made this element a stable element that could be activated in the ground and then hoisted and assembled in the final position. More than 100 years later, we see another example designed and built by the famous architect, German architect Frei Otto, and the contribution of Bureau Happold. And this building is called the Mannheim Multihalle. So it is an exhibition space covered by a shell structure. But this shell structure is a very particular, very peculiar one, because it is made of very slender timber laths. So again, structural wood. And these laths were joined in the ground using hinges and pushed up to the final position. And the whole grid was stabilized at the foundation, so joined to the foundation. And in this way, double curvature helped stabilizing the structure. And the final result, you can see this picture here. It is a very nice space where bending has been used to achieve the final shape of the structure. There are more other modern examples of this philosophy, of this kind of structures. And now we ask ourselves, okay, can we use UHPFRC to build bending active structures? And for answering this question, we need to look into the properties of the materials that are commonly used for active bending. And if in this case we have these two examples, the multi-hale I mentioned before, and another shell built more recently by the team of the École des Ponts in Paris and the firm TES. In this case, using GFRP as material for the rods. In both cases, we see that the ratio between the strength of the material and the Young modulus of the material is quite high. In the case of timber, it is about 2.5 times 10 to minus 3, and in the case of GFRP is 10 times 10 to minus 3. Why do we need materials with such a high ratio, strength to rigidity ratio? And the answer is that in principle, we ideally want the material to remain within the elastic range of strain and stress. And in order to have a better idea about that, let's look into the way cross-section works. And on the left, you see a cross-section, and imagine that it is working within the elastic range, and we introduce compression and tension, and we limit the amount of compression and the amount of tension to 25% of the ultimate strength of the material in order to limit long-term effects and such. You can, in this case, calculate the maximum curvature that the material is able to reach within these limitations. And we see that the curvature depends inversely on the height of the cross-section, the depth of the cross-section. Of course, a slender cross-section will allow higher curvatures, but it depends directly on the strength to rigidity ratio. And the result, you can see the result here. So we can reach this curvature in the case of timber. So this is the curvature you reach in the case of timber. Now, what about UHPFRC? We know that it has a very low tensile stress compared to the compressive stress, but we also know that we can pre-stress the concrete, and in that way improve the overall behavior. And the idea would be to pre-stress the material to reach about 1/3 of the compressive strength in compression, and also a kind of equivalent tensile strength, also about 1/3 of the compressive strength. And in that way, if we redo the calculation of the curvature by assuming this new stress distribution or approximate stress distribution, of course, this is not the real stress distribution in the concrete, but thinking on the concept, we see that we are able to reach a curvature which is quite similar to the one that we reach with timber. Maybe not so high, but it is at least comparable. So we see that UHPFRC should be considered a viable option to activate the bending of very slender flexural members. Now, what can we do with this? So let's build a footbridge, and let's look at another examples of bending active footbridge that have been designed and built in the past. So there is on the right an example again in Paris in the École des Ponts, and we have also tried concepts that are similar to the Paxton gutter beam in our laboratory. So this is a bending active bridge built with GFRP in our laboratory, in this case with very slender GFRP rods. And the question is now, can we replace these GFRP rods by UHPFRC cross-section? And can we develop and build a footbridge using this material for activating bending? Well, this is what we did, and this is what I am going to speak now about. So first the concept, then the behavior of the cross-section, the structural design, the production, and some conclusions and outlook. We wanted to build something very specific, and for this location, it was the way to access an experimental float prototype in Sagunto port in Valencia. We wanted a structure with a 2-year service life, so something very experimental, not very big. The span length is about 5 meters. The width should be around 1 meter because it is a small experiment. And there is some height difference between the float top level and the quay top level. We started with the concept. You see the bending active concept here. Let's cast the deck of the footbridge on the tension strands. Let's then transfer the pre-stress into the concrete. And once we have done this, we can, by means of a deviator, this vertical member, and cables, let's put some force into the structure and bend the deck and achieve a stiffer structure and very lightweight because it is made of a very, very slender UHPFRC concrete cross-section. The first sketches of the footbridge where we considered several cable arrangements, and we opted by the arrangement on the right, where the planes of the cable were slightly inclined outwards in order to reach a better torsional behavior of the structure, and also a sketch of the cross-section. And these are the main dimensions. So we are going to design and build a 5.4 meter span bridge with a total height of 0.6 meters and a camber of about 7.5 meters. So this is the bending that we want to introduce in the concrete element. So the concrete element will be, of course, built as a straight element, as I mentioned before. This is the cross-section with 2 lateral ribs with 3 pre-tensioning strands in each rib. The height of the cross-section is 6 centimeters, and the height of the central part is just 2.5 centimeters. So we are trying to reach the slender, very, very slender cross-section. If we look into the behavior of the cross-section, we can use a section model with the material properties for concrete that we get in our previous experiments. These are average properties from our previous experiments. And we are speaking about material with 150 megapascals compressive strength and peak tensile strengths about 10 megapascals, perhaps a little bit lower. The pre-tensioning strands have standard material properties that you can find in the Spanish or the standard or the Eurocode. And we developed a cross-section model. We coded the behavior of the cross-section, including cracking, including the material properties of concrete and of steel. And on the left part of the slide, you can see the moment curvature diagrams for this specific cross-section. And the difference between the several curves is the amount of pre-stress that we input in the cross-section. So the red curve is a cross-section with less pre-stress, and the blue curve is a cross-section with a higher pre-stress. Bear in mind that we are targeting a curvature of about 0.051/meter. So we are targeting at bending moments in this cross-section between 15 and 20 kilonewtons meter. After examining the properties or the way the cross-section worked, we found that the best target was to try to achieve pivots, simultaneous pivots in the upper, in the top fiber of the cross-section and the bottom fiber of the cross-section, and we could achieve this when the pre-stress was around 40%, 43% of the ultimate strength of the steel. Specifically, we are going to pre-stress the cross-section, each strand with 80 kilonewtons and a total pre-stress force of 480 kilonewtons in the cross-section. This is the front view, the plan view, and the typical cross-section of the footbridge, the proportion of the persons, and the design of the deviator, which is inclined outwards, and the arrangement of the cables with main external cables and also bracing cables, X-shaped bracing cables. And we used a simple frame model, 3D, but with frame elements joined by plastic hinges in order to model the activation process. And this is the activation process. So first we start by casting the deviator and in a reversed position. So the bridge is initially in a reverse position. The deviator is waiting on the bridge. We preload the bridge to reach deflection of around 100 millimeters. This is the worst situation for the structure. In this situation, the bending moment in the bent member is around 17 kilonewtons meter. And now we can, so the member is already activated, and we can install the main cables and unload part of the load that was placed in the mid cross section, and then install the bracing cables and fully unload this preload and reverse the bridge, so turn the bridge into the upright position. And this is the target shape, 75 millimeters of camber, corresponding to a manageable curvature. And the bending moments in the cross-section are even lower than the bending moment during the construction process. Now I want to show you some pictures of the production. So starting with the mold for the deviator and the pouring process for the deviator. You see here the mold and the counter mold. The final result with the anchorages for the cables and the connection rebars. And this is the pre-stressing phase for the deck and the formwork for the deck. Placing of the deviator and casting the concrete for the deck. This is the casting process. You can see that this concrete is work is very special. The workability is a special one, but it can be cast with very low section height. Here is Professor Serna hands-on in this process, and the final result. The deck, the deviator, and the cables, which are just presented. They are not really in tension. Now we have to activate the structure, and you can see that we have already loaded the structure in the mid cross section, and it is supported on the on each end, and it is of course reversed. We present the cables and we start spanning the cables and tensioning the cables and unloading the structure in this process, and the final situation with the cables in tension and the deck already bent, already activated. Now we are in the position to turn the structure into the upright position. This was done by means of a crane. In this sequence, you can see the whole sequence. And the structure is already finished and prepared for being tested. This is a test assembly using the support which will be installed in the final location. And we also did some loading tests using cement bags and with all the instruments to measure the deflections of the structure, which behaved as expected. Well, it remained to load the structure on a truck and transport it to the final location and install it. And you can see in this last picture the structure in the final position, and Juan and Carmen very glad standing on it daringly, because the railing is not yet finished, was not yet finished at that point. And well, so this is the prototype, and this is the result. We were quite happy that we could bend the concrete and achieve a really lightweight structure, a prototype. And what are the next steps? Our next steps are to build a high fidelity FIM model with Diana, also to use all the knowledge that was acquired in our research group that Eduardo and Juan explained before, and in order to first to assess and to check, verify the test results with our high fidelity finite element models, and with our view into the future to build a larger structure. And now I'm going to wrap up my presentation, and we have tested UHPFRC to the limit of its bending capacity while keeping serviceability conditions. We have demonstrated that it is feasible to use thin pre-stress UHPFRC slabs in bending for active bending structure, and we have demonstrated the potential to build very lightweight structures to reduce the consumption of materials, to reduce execution times. And our work in progress is processing test results and validating with a high-end finite element model, and of course testing larger scales, testing larger structures. And that's my presentation. Thank you very much for your attention. You see the pictures of the team who work in this project, and I remain available for your questions. Thank you very much.
Well, thank you very much, Professor Lazzaro. I mean, this was a very interesting presentation, and I must say that I'm looking forward to see the outcome of the finite element analysis with Diana. That will be very, very interesting. That's a very challenging project. So
I'm sure.
I again invite people to raise their questions. What I can already see coming in the chat box is a lot of people who are very interested, and they say a big thanks to you, Professor Lazzaro, for the quality of your presentation and the quality of your work. This is kind of constant in your group. I mean, the quality of the work is very well received. And we have a first question coming from Alok Dua. What type of failure modes are expected in such structures, especially if it's a student with deformation? So, yeah, the main question is what kind of failure mode are expected for these structures?
Yes, mainly because in this prototype we have only one activated member. It is a slab, but it is ideally is like a beam with a very wide cross section. The failure mode would most likely be bending failure of this deck. So this is for this particular structure. Of course, if we think of shell-like structure built with such members, we can have local failures, and this would be more beneficial in that case. So, but yes, on the other hand, we have checked and we have proved that the worst situation for the structure is during the activation process, and after the activation, bending in the structure goes lower. But if you load the structure, there is a balance. You have to achieve some balance, and also the amount of pre-stress was designed in order to try to avoid the brittle failure of the concrete. So we didn't want to input too much pre-stress in the structure, because it would then lead to brittle failure of the cross section, and therefore the relatively low pre-stress, 40% of the ultimate strength of the steel. Okay,
thank you very much. One more question from Juan Antonio Rodriguez. How valid is this design concept in terms of durability for pre-stress, pre-crack structures? So yeah, the core of the message is, how valid is this design concept in terms of durability?
Well, so the cracking in the concrete is smeared. So if it is well executed and well designed, you will have smeared cracking, and in this way there is no special concern about the durability. On the other hand, it is true that we are trying to reach the limit of the structure, and this makes of course, this makes the possibility to have wider cracks higher than in a conventional structure. In this case, it is also pre-stressed, so the cracks will tend to close up to some point. So I think that it is something that needs to be looked into, and therefore we said the durability of our prototype was 2 years, and it needs more research. But I don't think it is especially bad durability.
Okay, thank you very much. Maybe one last question from Rad Abdulaziz. Are there any studies for pre-stressed shell members with this ultra-high performance fiber reinforced concrete in your group?
Not really in our group. So this was the first. I know that Professor Serna, and he is going to speak about that. He has already pre-stressed very thin, other very thin UHPFRC members. So there is indeed experience in pre-stressing very thin members. Shells, so if you think about large shells for roofs and so on, I don't think we have that experience, but we are in the way to have it. So we have already done this with not so large elements, but it is feasible for larger elements, of course.
Okay, well, thank you very much. One more time, I must say that through the flow of questions, there's a lot of compliment for the quality of your presentation and the quality of your work. So this has to be mentioned. So I'd like to thank you one more time, Professor Lazaro, for this very nice presentation. And
thank you very much. Thank you.
We are going to move on with the last speaker. So Professor Pedro Serna was quite an experience because he was contributing to the first structural fiber reinforced concrete and ultra high performance fiber reinforced concrete applications in Spain. So he's going to be the next speaker.
Okay, thank you very much. Well, I think I am the last in this seminar. Then here, my idea in this presentation is to show our experience starting from the material concept that I will try to explain what we consider as ultra high performance fiber reinforced concrete in our experience, and I will try to expose some recommendation or some ideas for how to go from the material to the applications. I will try to do in a generalistic way, and then I will more try to transmit some concepts that can be useful for you, I expect. Where we are thinking in ultra high performance concrete that combines all most of the advantage of the new materials, new concretes in the last decades. Then is self-compacting concrete, is high performance concrete, high strength concrete, the ultra high performance concrete, and with a big amount of fibers close always. Then everything joined will reach these properties that we will use as ultra high performance fiber reinforced concrete. You can see that in the market there are other products in a similar concept, thinking in compressive strength or tensile strength, then from relatively low mechanical capacity, but always thinking in string hardening, in ductility, until very high strength concrete close to 200 megapascals and very big flexural tensile elastic limit. Then we will be in this center. Why in this center? Because it's difficult to obtain a good concept of application in the bigger, in the higher strength capacity elements, and because we want to be structurals. Then in this way, we start by here is our concept of ultra high performance concrete. And this is one recipe that we used. Of course, there are lots. What is the concept? We use aggregates, but aggregates means 2 millimeter maximum aggregates. But that don't mean that we only use a small or fine aggregate. We use a very good grading of aggregate from the bigger 2 millimeters to the finer. Finer, that means that we will go to elements, to materials even not clearly finer than cement. Cement is only one of the solid components. We use lots of cement, close to 800 kilos. We use silica fume, silica fluor, and of course the last generation of superplasticizers. Okay, that needs also a specific good or high energy mixer. High energy mixer is not necessary to use the best mixer in the world, but you need to combine the energy of mixing with the time. If you have a lower energy mixer, you will need more time. Okay, and of course you use lots of fibers. Fibers with this is one of those we use at this moment. 30 millimeters. You can go longer or shorter depending on your objectives. There are lots of commercial brands in the market, and you can select one. At the moment, we use our own recipe. Okay. What is the main properties of ultra high performance concrete? First, if you go to high strength concrete, it's easy to multiply the strength by 2, 3 to reach 100, 130 megapascals with normal concrete. Is the limit of 100 in the model code is a limit, but it's easy to super. If you introduce fibers, you can increase not too much the tensile strength. You increase the ductility of the cement, of the concrete. This is relatively easy. If you introduce self-compacting concrete, you can do clearly more workable. You can go to a slump of 10, 12, 20, to a slump absolutely 30 millimeters, then make it self-compacting. But if you use ultra-high performance concrete, you multiply by lots all the properties. But this number is not how you can increase the properties. This number represents more or less the price. This is the main property of this concrete. It's too much expensive, 10 times or even more than a normal good concrete. Then with that, you need to work with a clear cost-profit ratio. You need to optimize your design in order to take enough profit. Then you need to think in durability, you need to think in sustainability, and everything at the first moment. If you try to design like for normal concrete, you will never be competitive. Okay, other properties, compressive strength, yes, but you can super 150, but usually you are not able to design nothing where you need more than this level of compressive strength, because you need to incorporate the reverse inside. If you need to incorporate the reverse inside, it's very difficult to design nothing with a higher level of compressive requirement. You must be sustainable. That means you use 800 kilos of cement, but that means that you need to go to designs where your needs of concrete are reduced by 4, by 5 times. Otherwise, you are not sustainable. Then that might be, or must be also an objective, be in this level. But if you reach this level, you are sustainable also. Okay, and you need to combine workability. Concrete must to go inside, must to be possible to incorporate in your designs. Then concrete must to go around rebars, and must to go around reinforcement framework and reach all the positions. Okay, then that must to be also necessary at the design level, with the objective always of to be competitive with standard elements. Someone asked also for durability. Durability is also demonstrated. Of course, if you go with the limits of water cement ratio, or of the limits of permeability, or all the properties or content, cement content, you are clearly over all the limits. But in this case, you need to go even at another level. And we try, we work on demonstrating that this concrete, even if you are in cracked state, you can guarantee durability. And then it's clear those results are the corrosion intensity when you have a ultra high performance concrete in cracked state compared with a normal design of good high performance concrete. Then you must to work with that. And you must to think that your concrete, of course, your concrete without cracks is for ever after, but you never need to work for ever after. You need to consider your service limit, and then you need to consider and to work with reducing covers, reducing or consider options of working with the crack in serviceability, even for pre-stressed elements. If you do that, you can design in a competitive way. Okay, I talk on workability. Workability will produce fibers orientation, and this is a point where we need with what we will need to work. And you must to understand how your concrete is moving, because considering this movement, considering the presence of rebars, the presence of other elements in the way of the concrete, you will have some orientation. But this is only to consider that as you have lots of fibers, fiber will be always orientated in all directions. You can have a preferential orientation, but and you need to understand what. Okay. For instance, here you can see that this element is performed, is green. The color is because you can do as you want, but the movement is clear. But if you have reverse, you have a certain problem to advance the concrete. Well, this problem you must super. Super means to guarantee that all concrete is flowing in the bottom, in the top, and combine it after. Okay, that this is always possible, but you need to design your elements thinking on that, in the possibility of working or moving the concrete. Also, other properties that can be important is that your forward must to be strong. This is like a fluid. Then the pressure is like a fluid of 2.3 kilos by liter density. Then this is a high pressure in the forward, but you must to think also that your workability works always if the concrete is in movement. If you start the concrete, you have a reduced workability. Then to guarantee the movement of the concrete is not always easy. You must to be here. You must to be there. You can to go with the concrete to guarantee that everything is filled. And those options must to be also considered at the design level. Some aspects thinking on the properties. We talked of 102% of fibers. Of course, in the market you will find 2-3 higher volumes of fibers. If you want to reach hardening, you need to go faster. But with the 1.532% of fibers, this type of fiber, it depends also in the length or in the diameter of fibers. With this limits of fiber, we are in the limit of softening and hardening. Okay, but we need to understand that our objective is not to use this property, because softening, hardening, we are thinking in material, but our problem usually is to think on the structural ductility. Then we need to guarantee that, as Carlos says before, that the failure never happens with a sudden failure. Then this is a problem of designers, is to define what is the worst possibility of the material, of the structure. Okay, then important to consider what is the final working way. Okay, we talked on cracked state. Then if you do a flexural test, in this point, after a relatively low tensile strength, you have already cracks. You don't see, but there are. And only when you are here, when you are at the maximum flexural strength or close to the maximum flexural strength, you have a localized first crack. Of course, you can see that here you have one that is only one that increase, and at the end you have a big crack, but lots of small cracks are around your element. Well, we can define, go to the flexural to tensile strength, as Eduard commented before, and those are two important points. If we work on softening or hardening, but also at what level you finish your capacity of control the crack, because in this period you have micro cracks if you have hardening, but also if you have softening, and of course if you have softening in flexural, depending on the structural element, but even in this case, in this part, even if you have softening, you have multi-cracking. And it's easy to have multi-cracking only thinking in the variability of the sectional properties. You can see that in our main concrete, thinking of 160 kilos of fibers, we have a strain of crack localization close to 4 per mil, with big variability. The figures of Eduard can show some problem of credibility because the big variability, but even in this case, you have close to 2 per mil of strain with control crack, and working in a material that is in the limit of softening, hardening. Okay, with that is the element we work usually, and we work also with lower with more softening materials properties. Those are characteristic values. Okay, then the value that you can guarantee. You can see important those aspects. If you have hardening after cracking, you have always not a right line with hardening, because you have always cracking of material or matrix that is brittle and recover energy by fibers. Then you have always this behavior. If you have softening, you have exactly the same. Maybe you have higher down or increasing, but finally you have something like this. The problem is when you finish in your contribution, both in hardening or both in softening. And it's clear with only concrete, we are usually longer than the serviceability limited. You are close to 2 per mil in a strain. That means you will never work over that, because you have you never work in service with the yielding of your material. Then you have this problem or the decision to make. But after serviceability limit, when you are in ultimate limit straight, the contribution of fibers is very low. The fibers are to conserve crack control and to guarantee that in service you never have a crack localization. Well, I go fast to the typification, of course, thinking in compressive strength, to thinking in slow flow, of course, to thinking in residual strength, with tensile strength, sorry, and to thinking in the deformation that you can guarantee in service. Okay, those are to me the most important aspects to be guaranteed. Okay, to do what? To do elements like this, I saw that I will talk about our experience. That then this is not our experience started some time ago with something like this. A design for flooring. This is easy. This is only with a P element with only some reverse intention. This is a good way of working with a very low weight. Then this is a concept that you can design. It's easy to cast, it's easy to transport, it's easy to work. That was only a previous idea, but thinking on that, we worked on that. What is this? This is a pile sheet. In what condition? This is clearly high pre-stress. Okay, you have a very high amount of pre-stress in strength. For pouring, clearly you have your forward clear with the pre-stressed strength. You pour your concrete, a counterpoint, then in order to guarantee that the the concrete go up, and then this is easy to make. This is a good way to obtain a thin element. Is usually we work in 5-6 centimeters in order to take the place for rebars. And this element was used for as pile sheet, clearly, to be produced, and we tested that also in shear. This is the aspect of the shear failure. You can work with this concrete even in very thin elements, considering a very smeared cracking. Because of course those cracks are not easy to see if you don't take the surface width. Okay. Well, other ideas of replacing, by instance, big walls with only a thin elements of 2.5 centimeters. Also, the idea of 2 centimeters is because is the minimum you are able to do to guarantee the casting process. Okay, of course, this is here in my desk. You can come as you want. This only concrete. With this is even lower, only 1.5 centimeters. You can use it, not problem. Stairs made also close to here, so unlike thinner, but also without reinforcement, only with fibers you can do that. The final aspects you can do, you can obtain is clear. This is concrete. The color is only pigments, and you don't need any specific superficial treatment. You can work in a small with thin element like this, only fibers, not reinforcement, easy to perform only by pouring concrete. You need to guarantee that the pouring is continuously. If you try to start by here and start by here and joint in the center, you will have a problem. You will have a cold joint without fibers. Then you have a problem. But the problem is is because you don't perform well the concrete. These 2 by 3 by 3 square elements. This is, I think, 3 centimeters thick of only concrete. Was the platform for a bridge. Okay, then in this case, Juan started to comment about the Las Ovejas Rabin footbridge. Then that was one of the first proposal for us for a real application. Then we decided to work with a 135 megapascal compressive strength concrete with, of course, self-compacting concrete with flexural strength of 20 megapascal. That means close to 6-7 megapascal in direct tension as characteristic value. In this case, we worked with 35 millimeters length fibers because we wanted to do this element. This element, its ductility depends on the length of fibers. Then to do that, you need longer fibers. For other elements, you don't need so longer fibers, and you work with smaller ones. Okay, of course, with a very aggressive ambience and in colors, of course. Well, this is the design. Juan presented already the design. Is 45 meter length footbridge. We use with the concept of using the shape like a U-shape beam, but of course we replace the walls by a truss. Okay, this is clear. Advantage to multi-functionality of all elements. Then the railing is the compressive core, is the top cord. Then you have only here, only with that, is used for transmit all the compressions. And this part, only this part, is the tensile cord. This is the minimum place to incorporate all the pre-stressing strength. One problem, in this case, you can consider that this element is working in compression, and you need to incorporate a basic concept that you usually use only for metallic structures. Then backing is a concept that you must incorporate and you must to calculate. Is that why we incorporate in the compressive bars in the lateral, we introduce reverse to guarantee the stability, to support the stability in the buckling effects in the structure. Okay, of course we did previous tests to verify everything in the laboratory before. Then the casting procedure was clear by parts. To guarantee the good pouring, we transfer all the elements. This is the lateral with connection bar with joints, and we transport 45-meter bridge in a normal transport until the final position. Okay, this is one of the concepts. You need to consider, if you are working in a precast company, that the control depends, that the price will be different. When you work in steel, the material represents 40% of the cost. When you work with normal concrete, the material is only 5%. When you work in this type of concrete, the material represents 20% of the cost. Then you change a little, but the concept is similar. Other food bridge also close to Valencia that was made by RDC company and preferred company of precast that are colleagues here in Valencia, is a similar concept where we improve what? The concept of guarantee a easy construction way. Sometimes reducing too much the size is not a good way because you do more difficult the construction. And we introduce also other additional part. In this case, the railing was only in concrete, in this case in the access way, they are not a structural function, then they can be done only with concrete and without any reinforcement. They are working also in other this is a farm for muscles. Then that is usually done with wood, but we have not more wood here. Then we can do that with concrete, stressed concrete, thinking to work in the sea and with very thin pre-stressed bars. Okay, we tested, and I have only some minutes to talk about the final prototype, or the one of prototype of the project Resilience, where the objective was to work in durability. Then our objective is not only to have a very high performance concrete, but to have a very ultra high durable concrete. And in this project, we think it in the idea of to generate 6 prototypes, and we worked with Robert Maritime, our construction company, in designing a floater, a floater platform. Previous one was like this, made in steel, of course, with a design like this, external shell and internal ribs and rings. Well, why we can do that with concrete? In steel, you need a thickness of 26 millimeters. As steel has 3 times the weight, the density of the concrete, we can go to 3 times more in concrete to reach the same weight. Then, with this idea, we try to perform our design, something similar to that, with an equivalent thickness of 78 millimeters, produced like they produce with steel. They produce different elements and they connected after. Okay, then we need to work with that. The design is like this. In this case, we try to reproduce a floater like this, like the previous design, but go to a logical scale. The previous, the original one can be 30 meters high. Then for us, we reduce only a 5 meters, then a scale of 6 meters, but we conserve the shell, the external shell, with the same section, with the same radius, and with the same requirement, structural requirements. Then we reduce the volume, but we do not reduce the problems. Okay, then this is the design, 2 by 2 square meters, 5 meters, and with an arm that can be connecting different elements. In this case, only we finish here, and of course there will be a tube, a square tube, also with a thickness of only 6 centimeters. Okay, well, this is the design. It was evaluated, of course. That was produced by elements. Then this is the vertical ribs. This is the sectors of the rings that we perform. No one has reinforcement, only the main reverse vertical, only 1 bar of 20 millimeters in each side. All the other, only concrete. Okay? Then, of course, the arm has lots of reverse, but the idea is to put concrete by here, concrete go by here, and go to the top. And then we can guarantee that all concrete is well oriented and that you have not cold joints. We perform that. You perform the lateral in the same way that previous one, by counterpoint to guarantee the surface. This section is 2.5 centimeters. We do like a product of IKEA. We can do the montage of all the elements. We connect, pour the concrete in the section, and transport all to the foundries. Okay, then at this moment is there, and at this moment is there with lots of sensors to analyze corrosion. You can think that those elements, reverse has only in some parts 2 centimeters, 15, 20 millimeters of cover. And we are controlling time by time, no, minute by minute, the initiation of corrosion that, of course, it do not happen at the moment. We control the crack apparition, and then the idea with that is this is a different material. You need to think as steel, but you need to design as concrete. Think in the properties, think in high reinforced elements or not reinforced shells, and usually this material works very well as pre-stressed in order to take all the properties, all the capacity in compression. You must guarantee that good pouring control in order to guarantee a good orientation. Orientation will happen, but usually if you do well, orientation will be a good color for you. The material is not homogeneous, is not isotropic, but you can control that. Okay, then of course control the pouring, avoid cold joints, or reinforce those cold joints with reverse. Okay, we did other options, but I think we are out of the timing. This is the elements of the arm, a picture of the arm in the harbor of the prototype of resilience. you can see that we have cracks. Of course, we have lots of cracks. We have even cracks that in surface are close to 0.1 millimeters, but do not produce corrosion in rebars at the moment. Then, thank you for your attention, and if you have any question, I'm free.
Well, thank you very much, Professor Cerna, for this nice presentation and showing such a variety of application with this ultra-high performance fiber reinforced concrete. That was very well received, because I see a lot of positive comments in the chat box. Let me see. I have to go through the questions. We are going to pick up some of the questions. There is a question from Rafael Ruiz. So, what is the relation between bar spacing and concrete cover with the fiber length for the Las Overas footbridge? I'm not sure of the pronunciation. My Spanish is not that good, but
okay, yeah, no problem. Okay, in the first footbridge we use, as said, too long fiber. We use 35 millimeters, but in my opinion that was not necessary for that, because if you go after we never use more 35 millimeter fibers. Why? Usually we work with 15, 17, 20 millimeter length is normal for microfibers. I only recommend higher if you work in elements where you risk to have the failure by there, and you need to control ductility in your element. If ductility is guaranteed by rebars, that is logical, or by other redistribution capacity, I don't recommend to go longer. Then the answer is, in Las Ovejas, the maximum fiber was 35 millimeters, and the cover may be close to 2.5 centimeters. Okay, that was reality. My recommendation is don't do like this. We learn time by time.
Absolutely, that's probably the best conclusion. One more question, which is actually a very practical question from Had Abdulaziz. He says that normally the surfaces of this ultra-high performance fiber reinforced concrete are really rough and can be even painful. So how can you make, how do you deal with this aspect when you make furniture? Because in one of your examples, you were showing some seats and tables.
No, for us, the surface is never a problem. Of course, if you work against a forward, your surface will be exactly the forward. Any problem you have in your forward, you will have in your surface. But you will never find fibers in the surface if the forward is good. Okay, then you can reproduce perfectly. You saw in Las Ovejas or in other elements, when we do the platform, we use usually the forward surface as the top one, as the better. But the result is perfect. You have no problem, and your roundness can be reproduced as you introduce in your forward. Okay, if you have a finishing surface, you can find some fiber in the corners, not more, only in the corners, that you can retire. You can avoid clearly by brushing or by, maybe it's good to incorporate thinking in practice with fire and brushing in continuity. Then fiber disappears fast.
Okay, well,
I don't know if
it's yeah. I mean, your answer is satisfactory. I mean, we get positive feedback. So thank you very much for that, Professor Cerna. And there's a lot of comments coming, positive comments about your presentation. I cannot read all of them, but your presentation was very well received, and people acknowledge the quality of your work. So,
okay, thank you.
Well, thank you for these presentations. Due to the timing, I think we are reaching at the end of this webinar. So before I close the session, I quickly want to mention that you can find the detail of this presentation on our website, and you can also access the contact details of our speakers. So if you just expand the name of our speakers, you can find their contact details. So if you want to address questions directly to them, or if you want to share your greetings with them directly, you can do that. You can find this information on our website. I'd like to mention that this seminar is recorded, and it will be published on our YouTube channel that you can access from our website. So I would say keep an eye on our YouTube channel. It will be available in the coming days. We need just to do a little bit of post-processing. And I would say that, yeah, sharing the feedback I could read, I'd like to say a big thanks in the name of the audience to our speakers. So I would say big thanks to Dr. Eduardo Mezquida-Alcaraz, Professor Juan Navarro-Gregori, Professor Carlos Lazzaro, and Professor Pedro Serna. I mean, this seminar was only possible thanks to your very valuable contribution. So in the name of Diana here, I want also to thank you for that. And I want also to associate my colleague Maziar Partovi, who couldn't be there unfortunately today, but he initiated this seminar, and he has been the contact person, and he organized everything with you gentlemen. So I'd like to say a big thanks to him as well for this organization. And of course, I'd like to thank the audience. I mean, a lot of people show interest for this online seminar, so this was very well received, and there were a lot of positive feedbacks, especially about the presentations. So altogether, I think it was a very successful event. So I'd like to thank you all for that, and I'm going to close this session. And soon you will be able to watch this recorded event on our YouTube channel. Thank you very much, and keep an eye on our website. Thank you.